Hi everyone, as he said, my name is Nina and I work at Facebook. And I would first like to congratulate everyone here on making it to the first talk of the day, except for the people with jet lag who are just cheating. So I have a tendency to speak pretty fast when I get nervous, and I get nervous when a lot of strangers stare at me. So if that starts to happen, just wave me down and I'll slow down again. So I'm here to talk about how Facebook disaggregated our network. And I work on the software that runs the custom switches in our network. And I'm going to go over the process of why we decided to do this, the steps along the way, and of course, all of the things we wish we knew at the beginning. So to begin with, if we're going to talk about networks, we may as well talk about the social network. Facebook has a lot of users on a lot of different platforms. And a lot of users in a lot of platforms means a lot of traffic. And in general, when people discuss networking and traffic, they're talking about egress, the number of bytes that leave your network and go out into the wider internet. However, at Facebook, we have far more traffic running through our internal network, through our data centers and our backbone. And this is traffic that never even leaves our network. And this has led to a bunch of design decisions in order to help us scale and in order to manage this network at scale. So I'm going to start off by talking a bit about how we set up our data center networks. And this includes some terminology and descriptions for anyone who might not have had to deal with things at this sort of level. So these are racks. They're a bunch of servers stacked on top of each other and stuffed into a metal chassis. And right at the top, we have the aptly named top-of-rack switch. And this basically provides connectivity to every server in the rack, as well as from those servers onwards to the rest of the network. And generally, the rest of the network looks something like that. The top-of-rack switches connect on to the data center topology, which then connects to the internet and other data centers via dedicated backbone. At Facebook, our topology is called Fabric. And this is a very clear and simple illustrative picture. So in order to get a better idea here, let's look at a slice of this. Also, very simple. Right at the bottom, we have top-of-rack switches, and we have no redundancy at this layer. So if a top-of-rack switch goes down, it means the entire rack of servers goes down with it. One layer up, we have fabric switches, and each top-of-rack switch connects to 4 of these in order to have some sense of redundancy. And the 4 fabric switches and all the rack switches they connect to are referred to as a pod, and this is kind of our unit of deployment in our data centers. The fabric switches go on to connect to multiple spine switches, and so on until we get to the switches that connect multiple data centers together, as well as to the wider internet via the network backbone. Okay, so you may be asking, why does this need to be so complex? And this is basically answering the question of, well, the problem of how we connect hundreds of thousands of servers in some sort of efficient way. If we had a switch that had 100,000 ports, this would be a lot easier. We'd just connect all the servers directly to the switch and kind of be done with it. But we don't have that sort of switch. And so we're left devising ways to provide the best connectivity that we can. And a nice benefit of this sort of really meshed network is that it doesn't matter where a server is, it requires the same number of hops to go from one server to any other server in the same data center building, which makes planning for where to put your services a lot easier. Okay, so to summarize the main points here, our data center topology is hierarchical, and it consists of multiple layers. There's redundancy at all layers except the bottommost layer, and there are different requirements for hardware and software depending on where the device is positioned. And by different requirements, on the hardware side, I mean things like the number of ports a switch has, or the different port speeds that things are able to run at. On the software side, this is protocols or various networking features, and of course scale. And by scale, I mean the number of routes that can hold in its route table. So this has been a pretty quick run-through of our data center topology. And I know people are not here to listen to me discuss data center topologies, so I'm going to move on pretty fast onto the actual switching stuff. Beginning with the old days, how we used to do things and why we decided to go our own way. So as I mentioned in a previous slide, we need a lot of different switches, depending on where in the data center topology they sit, and they all have roughly different requirements. And previously, in order to meet this, we had to work with several network vendors in order to find the right device for the right spot. And network vendors typically bundle their hardware and software together so that they provide a complete customized solution for their customers. This meant that in our data center network was pretty heterogeneous. We had different devices from different vendors that got configured in different ways, that allowed you to collect and aggregate metrics in different ways, and of course had different levels of customization. The one thing that they did have in common was that there were no major software upgrades during their lifetime. Generally, apart from the occasional bug fix, you'd bring in a switch, dump it in, and leave it there until it got decommissioned a number of years later. And this meant in order to operate these sort of different devices, we needed teams of network engineers in order to write tools and scripts and that sort of stuff to get everything to work together as one network. And as the number of devices and the complexity of our network increased, this just wasn't scaling. So as I mentioned, there were a couple of problems with the scaling. Having to build more and more automation was more and more difficult because our hardware was heterogeneous, and we had limited access to the switch internals. Not only that, we couldn't change what or how things came out of them. When we had to fix a bug or needed a new feature, we generally had to wait a long time to get the new image from operators. And once we got the image, we'd often find even more bugs because they'd bundled in some extra features or there were other bug fixes, and these were now interacting with our network. So there were more iterations and more waiting for the vendor to provide an image. And once we finally got this image, the upgrade process was really disruptive. As I mentioned, top-of-rack switches have no redundancy, so you take the rack offline for minutes, hours, whatever was required for that upgrade. And that meant that we had to roll these upgrades really carefully. A good example of this is a couple of years ago when we upgraded to IPv6. At that point, vendors had different levels of IPv6 support, and the majority of people still ran IPv4. This meant that it took a cross-team effort and years of work in order to get there. And this started with first testing every single different device in our network. So that's every different vendor and every device type they provide that we have running in our network. And when we found issues, we'd have to go back to vendors, wait for fixes, and kind of restart this whole process of testing again. Once we finally had images that we were confident in, we started an infrastructure-wide process to roll them out, working really closely with service owners because we were going to take their racks down. And this was, as I said, particularly painful for top-of-rack switches. Overall, this process took years and is really not something we'd like to repeat at any sort of cadence. So the last problem that we ran into with this sort of thing for scaling was that we wanted to try new things to get ahead of our network growth. And this includes things like experimenting with new topologies or new protocols and improving and creating more detailed and customized monitoring to better build automation for our network. And all of this was impossible without wider vendor support. And we just weren't getting that support. So we needed something else. So we decided to try something new. We decided to separate the traditional networking components. Generally, you have vertically integrated hardware and software. And instead, we tried disaggregating them. And this allows us to replace the hardware and software independently as soon as better versions become available. And it also gives us control over both sides, which allows us to better scale our infrastructure. And while future workloads are pretty hard to predict, we're able to adapt to changes through disaggregation. By having modular hardware, we're able to apply the most efficient configurations without having to reinvent or redesign the hardware we're using. And finally, we open sourced all of this, as well as in terms of the hardware, as well as the key low-level software component, is as an effort to kind of improve the community around white box switching. And this was all done through the Open Compute project. Okay, so I've dealt with the why, and let's talk a bit about the what. So this is our first device. It's a top-of-rack switch, and we call it Wedge. It took about a year with small teams of hardware and software engineers to get into production. And we decided to start from the lowest layer here because it has the simplest hardware and software requirements. Once we were confident in Wedge and had it in production, we decided to tackle the next layer up with disaggregation, of course. So we took 12 wedges, stacked them together, stuck them into a box, added some wiring, some BGP magic, and our first chassis switch 6-pack was born. Since then, we've been pretty busy. Following on our work on 40 gigabit a second top of rack and chassis switches, we moved to 100 gig to meet the growing needs of our network. And this included a 100 gig top of rack switch, as well as a 100 gig fabric switch, which we call Backpack. And our latest device is a new top of rack switch, which includes a bunch of extra security features like a TPM. Okay, so one thing that's interesting about this whole progression is that the software that we wrote in order to run this, the software called FBOSS, evolved alongside our hardware, and we essentially run the same version of the software on all of these devices. In terms of where we are in production, the majority of our top-of-rack switches are now wedges, and at the beginning of the year, we started rolling out our Backpack chassis switch. So now that I've kind of laid the scene here a bit, let's take a closer look at the hardware itself. So we wanted to leverage other open compute components, and with the idea to design this switch to be similar to servers. And this means more memory and a stronger CPU than you would typically find on vendor devices. And the reason why here was because we wanted to run a lot of the same software that we run on our servers, but on our switches. We essentially wanted our switches to be servers. If we take a look at the basic hardware available on the board, we have the ASIC, which is the specialized hardware responsible for packet switching. And this is connected to a microserver via PCIe bus, and the microserver has a BMC, of course, to monitor it. So we figured we already knew a lot about managing servers, and that we could leverage this knowledge and information and these tools in order to better manage our switches. To do this, we made the microserver look as much like a prod server as possible. So it runs our standard CentOS image. It has all the same management applications as we see on our production servers. So this includes things like logging and configuration management, metrics, and so on. And as a software engineer at Facebook, if you had to somehow manage to log into a switch, you'd have a pretty hard time telling it apart from one of our traditional servers. In addition to all the management processes, we also have the two key packet forwarding processes, BGP and the FBOSS agent. The BGP daemon implements the commonly known protocol and feeds root information to the FBOSS agent. The agent, in turn, programs this information into the ASIC using our chip manufacturer's SDK, in this case, OpenNSL. On the software side, we had a couple of goals, which can be summarized as writing simple software that we're able to upgrade often and that piggybacks off as much Facebook infra as possible. And this was because one of the big aims of this project was to prioritize operations over features. Most vendors are pretty much concerned with features. While we are an operator first and foremost, we much prefer simpler and easier to use devices over those with lots of features. Lots of features mean interactions between them and a lot of difficulty when debugging things because you're not sure what exactly is happening under the hood. This means our software supports only the things we need. IPv6, the protocols we actually use, as well as only the networking features required by our network. This clicker is having some problems. So this kind of shows what I mean when I say our switches are essentially servers. But it doesn't really answer the question of the operational side of running switching as a service. And this includes the prod realities of deployments and monitoring, configuration, disaster recovery, and so on. And while we get a lot of it for free by using Facebook infrastructure, there's a couple of things that need to be switch specific. First of all, in order to have any sort of reasonable update schedule, we need a way to update our software without having any effect on forwarding. So as I mentioned, our top-of-rack switches have no redundancy, so we need a way to upgrade the software on them without taking them down or affecting the sending of packets. And in order to manage this, we use a feature from our chip manufacturer Broadcom called Warm Boot. This allows us to restart the forwarding process without losing any of the hardware state, which is pretty cool. This moves us on to the next step, which is ensuring the correctness of our regular updates. And this allows us to update all of our devices fleet-wide every 2 to 4 weeks. And we do this using standard large-scale processes. So we canary test and monitor daily. When we're comfortable with a binary, we push it to a small percentage of switches in the least vulnerable parts of our network and monitor. And we continue this process of push a small bit, monitor, and continue until we're fully rolled out. And we have really strict margins of error here, because a single top-of-rack switch down isn't just one device down, it's every server in the rack down, and people get pretty unhappy at that. So we investigate most of the failures we see, and we're very sensitive to any kind of disturbances in the force. And finally, there's planning for the inevitable. As we know, in any large-scale service, failures are common. And the question of widespread failure is when, not if. So we're continuously investing in better and better test systems as well as disaster readiness. And if anyone saw the talk yesterday, we frequently test our disaster readiness. And the goal here is that should the main forwarding binary have some sort of issue, it can recover as quickly as possible and continue forwarding packets, and we can come back later and figure out what actually went wrong and solve that. And while we use a lot of Facebook infra, we don't fully rely on any of it. This means that if there's some issue with one of the components running on the switch, it doesn't matter. We can continue forwarding. We may not have logs, but at least the packets will still be going where they're meant to. So at this point, it makes it all sound like it's been smooth sailing all along. We did our job, we went home, nothing left to do. Tacked an ASIC onto a server, and voila, magic, everything was fixed. But as with most things in tech, the truth is a lot more nuanced. So servers, switches, as much as we would like to pretend that they're servers, they're not quite. They have different uptime requirements, different reliability guarantees. They're vastly underpowered when compared to traditional servers, and they have a much larger blast radius. And so while in principle they're servers, in reality they need a couple of alterations in order to be managed effectively. And if I'm honest, the process of managing servers is actually pretty hard. The field of distributed systems is kind of like thwarting entropy, trying to make sure all of your servers are doing the right thing at the right time simultaneously. And so managing a large number of servers is pretty difficult, even if it is something that we have a lot of experience with at Facebook. And since our switches are now servers, they need a lot of the same maintenance. And this includes things like operating system and kernel upgrades on things like a top-of-rack switch, which can't have any downtime. And generally, these sort of upgrades require a reboot at the very least, and varying amounts of downtime for installation. And all of this is pretty disruptive. So in order to do this seamlessly, we did a lot of work to improve the drain automation available. And by working closely with service owners, as well as the people who are providing the updates themselves, we managed to get this process that took years for IPv6 down to weeks. And this allows us to keep our underlying systems current without unnecessary downtime or extra effort on the part of service owners. And it's not just the underlying system that can kind of affect our workflow. As I mentioned earlier, we have a bunch of these management applications running on our switches. And they're also updated and tested and changed all the time. And they've traditionally only run on servers, which have fairly different requirements, as I mentioned. And this is a completely different risk. These have complex internal dependencies, and the software is changing faster and faster, and they have dependencies on shared binaries that evolve independently. And this is, again, why we have such a focus on comprehensive testing and disaster recovery. It also means that we've had to work with the services we depend on in order for them to handle our specific resource constraints, as well as to make sure that any big changes are tested early and often on switches. Okay, so managing servers is hard. What else is hard? Well, hardware is hard, pretty unsurprisingly. Another thing that servers don't have, of course, is an ASIC. And we've seen some pretty bizarre hardware interactions between these. For example, we had an LLDP utility that, when run, would occasionally cause our microserver to lose all contact with the ASIC permanently, like that switch bricked, done. We discovered that there were different implementations of the PCIe spec between our CPU and the ASIC, and this occasionally caused all interrupts from the ASIC to stop. So we've definitely had an array of interesting hardware issues to solve. And these are pretty difficult to diagnose and often require a lot of cross-team collaboration. And this includes things like getting switches from the data center to our labs, between software engineers who normally identify the problems and hardware engineers who have to drill down, and of course between Facebook and our various chip manufacturers. And this is something we've definitely gotten better at over time. It's required us to build up expertise in new areas, as well as improve and harden our testing and burn-in process. And a lot of this boils down to the fact that change is hard. By overlapping large-scale service building and operating with traditional networking, we've required a lot of human adjustment on all sides. So when I say change is hard, what I really mean is people are hard. And one thing that really surprised me when I joined this team was how many different people in different backgrounds and different roles were required to interact with these switches during their lifetime. And this includes people like the hardware designers who actually design the hardware up front. And I don't mean just the board, there's also things like the sled to get it into the rack and so on. There's the people who test and figure out what are the best optics for us to use, the people who go out and source all of these components, arrange manufacturing, the people who write at the end open source all of our stuff, the people who write and deploy the software or set up and configure the provisioning, monitor the overall network health, are worried with the overall network design, set up metrics and configuration, log in and check switch state, and fix and replace them when they break. They're the people who actually cable up the devices, clean optics, erase hard drives, and of course the service owners who are pretty unhappy when you stop sending their packets. And so this has required a constant cycle of feedback. For example, hardware engineers are generally concerned with getting everything to fit in a box. They have a particular form factor to match, and so they're not really interested in adding more memory or a bigger CPU. As software engineers, we'd much rather we had some more breathing room. And so this has been an ongoing discussion as each of our wedge generations have evolved. As a software engineer, I don't really think about the process of bringing a switch up in the data center. And our switches arrive unprovisioned, and we provision them over network because we've got our specific Facebook software. And this is very different from vendor switches, which kind of arrive ready to be plugged in. And without any external signs, it can be hard to tell whether things are wired up correctly or whether the cables work and so on. And so we needed the people in the data center in order to tell us about this sort of problem so that we could make sure that the LEDs were useful as soon as possible. Or in the case of network engineers who are used to the interfaces that vendors provide. As software engineers, we had to either mimic these interfaces or show the value of doing things differently. Not only that, but network engineers are used to working with vendors. And they now needed to get used to working with the plethora of Facebook teams. And we unfortunately don't take them out for dinner nearly as often. We needed to chat to the people who monitor the network about what metrics were most useful to them. And they in turn had to get used to their previously static switches suddenly changing underneath them. The question where we introduced Chef to them was, well, the conversation we introduced Chef was a pretty interesting one. Hardware engineers need to get used to supporting the devices they design in production. Software engineers who are used to owning and kind of designing for their services end-to-end need to start to design tooling for people without any sort of dev background so that they're able to manage these devices effectively. And service owners, essentially our users, need to deal with the fact that just like there are no special servers, there are no special racks. And all of this sounds like a lot, and there's a really big panic on that screen over there. So it's worthwhile to get back to why we started all of this. And we're essentially doing this to make our lives easier, and to make the lives of everyone involved in the lifespan of switches and the network as a whole easier. And the easier the periphery of our jobs are, the faster we can move and the more time we can spend working on actual interesting problems. And this has meant a lot of collaboration, a lot of talking to people and giving and taking feedback. And if you've ever visited the Facebook campus, you'll have noticed that it's plastered in posters. One that's particularly important in this project is this one. And a lot of the project's success is actually hinged on this. So are we happily ever after? Let's settle for happier. Teams are much more integrated now. We have the operational load shared between multiple teams across multiple roles. And new projects include all sorts of people from the very get-go. And we're definitely learning from our mistakes here. So while things aren't perfect, this shift has brought a lot of benefits with it. For starters, we can move a hell of a lot faster. Bug fixes can be deployed quickly because we already have all of the existing tools and infrastructure in place because we do regular updates. And in the case of emergency, we could even deploy a fix fleet-wide on the same day. And we really do have a poster for every production emergency. Not only that, but it opens up a wealth of new possibilities. We can experiment with new protocols easily. We can add more comprehensive monitoring that covers our specific networking needs, and with this, provide smarter operational tools. And of course, we're always looking for new places in the network that can benefit from Wedge and FBOSS. And while this was a highly technical project that had a ton of risk in it, we didn't succeed because we had the smartest people or the most innovative ideas, with no disrespect meant to my colleagues who are both very smart and very innovative. Rather, we succeeded because there was a concerted effort from a lot of people in order to make things better, not just for one specific group, but for everyone involved in the process. And working together like this, disaggregating the network so that we can build it for people rather than the other way around, has indeed made life a lot easier. Thank you. And I think there's time for questions.
Thanks, Nina. Thanks, Nina, for a fascinating talk. It's Q&A time. We would like to ask that you speak loudly and clearly into the microphone because we are broadcasting. First question, please.
Hi, excellent talk. Thank you very much. The presentation made everything look happily ever after. I'm actually wondering what was some of the stuff in this project that wasn't happily ever after, because I'm sure there are some things that didn't get into your slides that were the opposite of everything worked perfectly.
Sure. So I kind of touched on a couple of those. At least as a software engineer, the thing that's affected me most strongly is the hardware issues. We're dealing with hardware that isn't running at the scale of, say, our servers, so it's just not as well tested. And getting into the heart of these issues requires skills that, as software engineers, we don't necessarily have off the bat, and hardware engineers don't have the software engineering skills, and we've had to, often the bugs have come down to things in the actual chips, which mean we then have to sit and work with vendors for as long as possible to try and figure these out. And I covered 2 cases, but there have been a lot more of these like very specific to our certain hardware, which as a software engineer means getting used to kind of running on untested hardware, which is a new thing. You just kind of assume everything under there works fine and it's going to be okay. There's also, as I mentioned, the whole like having to do disruptive upgrades, because service owners, they haven't always planned the best, so they have things like somehow have managed up with like multiple masters in the same rack or something like that. And it's made the whole process of doing these more disruptive upgrades, which in essence we should be able to do easily because no server is special, require a lot of work. And so when I say we work to improve the drain automation, in many cases we had to help service owners actually write drain automation because they were like, what is this stuff? Why would you need to do this? You know, so it's, as I kind of said, it's all around people problems, you know, and working with people in the data center and people who are traditional network engineers, they don't necessarily have an understanding of like the software flow of things. So they are very anxious about a lot of the stuff we do. They're like, well, there's this bug and it's never going to be fixed, because if they're used to hardware timelines where if there's a bug, you're waiting like months. So there's been a lot of like placating and adjusting and making friends with. Yeah, so that's kind of the thing.
Hi, Nina. Thank you for the great talk. You had a slide that showed everyone that touches your network equipment. I did not see anyone from security listed on there, and I was wondering, when does security come into this process?
So because we run, sorry, there's a Facebook employee in the front there. Because we run a lot of the same infrastructure as the rest of our production servers, we get a lot of the security for free. So our services all have kind of security baked into them so that they speak to each other over encrypted channels. And we have a whole branch of network security that is involved with the kind of wider network overall. They're not generally involved in the bring up of a new device, but it's definitely a concern, seeing as our latest device has a TPM on it and that sort of stuff. So we get a lot of it from Facebook, and the bits that we don't get, we have a dedicated team for, and I should probably have added that to the slide.
Thanks.
As more and more of the networking gets pushed into software and away from hardware, what does that mean for the future of networking vendors? I mean, what's the place for them in the new world other than sobbing at the hotel bar?
I mean, this is not getting rid of networking hardware completely. Like, we still use a Broadcom ASIC. The majority of packet switching is done in hardware.
Yes.
I'm probably not allowed to comment on Facebook's position on other network vendors, unfortunately. Yeah.
So I have to assume at some point in time, before you had this hardware, someone would have been like, hey, we should make our own switch, and somebody else was like, you're insane. Did you guys develop the expertise required to do this in-house, or did you like literally purchase wholesale like people and technologies from other companies and be like, come to Facebook and do this here? How did that go?
So the majority of the software engineers, there were like 3 people who started this, and they were like, we believe in this. We're going to do this. And they were all in-house. They were already hired and kind of working in this area. And since we've already been building hardware for quite a while, because we've been building our servers for even longer, we had a bunch of hardware people on site who like knew how to do these things, connect the transceivers and that sort of stuff.
Oh, that's very cool. Thank you.
Yeah, because you control both the pieces of the thing, right? Basically the hardware and the software. How do you if there's a performance issue, how do you know it's hardware or software? What kind of metrics do you have to pinpoint it's here versus here?
So obviously we have all the kind of software related metrics that any traditional service would have. And we're also able to pull a lot of hardware specific metrics from the device itself. So we can tell things about like the memory utilization of various buffers and like how much of the TCAM memory is full and how many cells are being used for this queue compared to that queue and that sort of stuff. So we can generally isolate it down. If we find that in our software it's taking a long time in hardware code, then because we also have access to all of the hardware code, it's all under NDA, but we can read the hardware code. So when it starts to call into like actual system calls into the device and like lower level stuff, we can be like, hey, this is the choking point. And Broadcom as our chip manufacturer is actually pretty responsive to these things when we call them up and they're like, hey, there's a problem.
Thanks.
I just had a question. We see some of these big cloud providers now taking their internal technology, turning it out and externalizing it and trying to generate revenue from it. Is this ever going to be something where Facebook has got such its own proprietary networking stack that so many other businesses that are still stuck in on-prem infrastructure that can't quite embrace other people's clouds? Would you guys ever consider becoming a network vendor, or is that too?
So we provide all of the plans, like you can build a full switch. We're definitely not interested in building them ourselves. We get other people to build ours, and you can, for example, buy one-offs of our wedge switches fully built and everything. And the idea here is that we want to provide as much of, and we do this for not just our switches, but our servers and a lot of our core services. We want to provide as much as possible open source so that other people can kind of benefit from what we've gotten, because we really believe in growing community around this stuff. And network switching has traditionally been really black box. Like, you just don't know what's happening in there. So, and there are a couple of companies working with us on this to try and open all of this up. And we think it would be better for the whole kind of ecosystem as a whole.
So like the OCP? Is it,
yeah, so this is all part of OCP.
From the software perspective, the stack that you've built, is that also made available?
Yeah, so the FPass agent is on GitHub. I have some links at the bottom there if you're interested in that
Thank
stuff.
you.
Sure.
So I'm glad we didn't make you nervous, because that was a very well-paced presentation. A lot of information you got across to us. Just out of curiosity, you talked about the disruptive upgrades, the software upgrades. So the telco industry has always faced that as well. And as far as I know, any large telco switch has 2 processors, 2 complete systems on board, an A and a B. And they go ahead and they do a midnight switch over from one processor to the other. And they also do their upgrades through the down processor gets all the upgrades, and then they go ahead and do the switch. I'm sure you all considered that, given the size of your teams and whatnot. Out of curiosity, why did you elect not to go ahead and take that approach?
So it boils down to cost. And generally, when people think about cost, they're like, oh, there's another top of rack switch. But this includes having extra NICs on every single server in the rack, as well as double the amount of cables running from each server up to the top of rack switches. And this means that we decided to rather kind of swallow these reliability issues and improve our software to handle them. With the idea being that any server should be able to go down at any time. And we needed some work with service owners to get to that point, but at least now, after having successfully rolled out operating system upgrades and kernel upgrades, we're pretty close to the point where we could take down any rack. So it's not as much of an issue.
Okay, thank you very much.
Sure.
Hi, thanks for the talk. I was wondering, how reliable are the top-of-the-rack switches, and are you planning to introduce some reliability in there?
So they're pretty reliable. We run the majority of our network through these top-of-rack switches. Yeah, everything is designed to make sure that whatever problem happens, we're able to recover it. And we legit run very large-scale disaster recovery exercises to make sure that should everything go bad, we can recover from it. Yeah. Generally, when we do a deployment, to give you kind of more concrete things, we see less than a 1% failure rate of transient failures and less than 0.1% of permanent failures. So transient failures would be like a port flat. Yeah. Anything else?
If that's it, and there are no further questions, then let's give a warm thank you to Nina.